The dynamic system we chose is the fly-by-wire flight control systems for aircraft. So the fly-by-wire system is a control system that replaces manual control systems with an electronic interface. For this project, we're focusing on the pitch control. The features include the sensors, which take into account the pitch angle, pitch rate, altitude, and speed. Other features include the control surfaces, mass distribution, and actuators.
Here is the most basic equation of motion in a discrete behavior for the aerodynamic moment due to its elevator or pitching moment surface. This includes 1/2 times rho times velocity squared times the wing reference area times the chord length. Typically, the deflection of the control surface used to create a pitching moment is also added to the end of this equation, and is implemented by the control law to adjust the control surface orientation as needed. Also, this dynamic system uses equations part of a continuous time model because it is a dynamic system. However, in practical applications, such as fly-by-wire systems, these time models are often discretized for implementation in digital controllers. This process involves sampling the continuous time signals at regular intervals and then updating the digital controllers. For our inputs, outputs, and measured, for inputs, the system include the current pitch angle, angle rates, velocity, which are measured by the sensors. The pilot then chooses the desired pitch angle to be at. And then outputs, the system outputs the pitch angle desired by the pilot. And then what is measured is the pitch angle, but also how said pitch angle corresponds to the final orientation of the aircraft, and then returns these values to the pilot and feedback loops for adjustments.
Okay, so the feedback loop system comprises of 2 feedback loops. The first feedback loop takes the pilot's inputs for desired pitch angle, then uses control logic to change the elevators accordingly. After this, the output is measured with the sensors on the aircraft for pitch angle. This measurement is then fed back into the control loop until the pilot's desired input is reached and measured by the sensors. The second control loop involves the pilot. Once the first feedback loop terminates at the desired pitch angle, the value is again measured by the sensors and displayed to the pilot. If this value does not meet up with the pilot's requirements, then a new input is made and process begins again. So for this problem, there are about 4 coordinate frames involved, but some more minor ones that we didn't include. The first is the body frame, which is centered at the center of mass of the aircraft, and the x-axis points longitudinally, the y-axis points towards the wings, and the z-axis points towards or away from the center of the Earth. The northeast down frame, or NED frame, is the navigation frame of the aircraft. The x-axis points north and the y-axis points east, while the z-axis points downwards. The ECEF frame, or Earth-centered, Earth-fixed frame, has a z-axis pointing towards the North Pole, x-axis pointing towards the prime meridian, and the y-axis completes the orthogonal basis. The origin is fixed at the center of the Earth. And lastly is the stability frame, which is aligned with the aircraft's body frame and is modified to match the stability characteristics of the aircraft. The axis points in similar directions to the body frame. And here we have 4 different examples of the frames just described. The first one is the northeast down frame. The second one, figure 5, is the ECEF frame, or Earth-centered, Earth-fixed frame. The third one is the body frame. And finally, you can see the stability frame is an only slightly offset version of the body frame.
So here we have the schematic block diagram, the inputs being the pilot and whatever is measured by the sensors, which then go on to affect the onboard computers, which affect the control logic, the actuators, and then the airplane, therefore achieving the desired pitch angle.